Okay, so I'm going to be going over the FRQs. I'm going to go rather quickly in order to finish before Pi block. So for the first one, we're actually going to be doing this as a lab today, so we can make sure we understand how to write the differential equation. So we covered it in class, but I want to clarify where the minus sign comes from for the exponential equation, right? When we look at the current through the inductor as a function of time. So here we're going to close switch X at time equals 0, and then we have just the battery, the resistor, and the inductor. Switch Y is going to remain open. All right, so what we need to do is we need to set up our differential equation. All right, so here we have our loop rule, and we know that the EMF is going to go up via the battery, and then it's going to drop across the resistor. And then here for the inductor, to clarify, this here is going to be the positive end of the inductor, and that there is going to be the negative end of the inductor. And since we're drawing our loop clockwise, I have current coming in this way, so it's going to be minus I dL dt for the potential drop across the inductor. So let's set up our equation. So epsilon minus IR minus L di over dt equals 0. Okay. So then the EMF of the battery is equal to IR plus L di over dt. And let's make sure this makes sense. So I really want to emphasize this point here. Di over dt is going to be positive, right? So initially an inductor opposes change in current. All right, so the current through the inductor at t equals 0 is technically 0, but it's going to be increasing with respect to time. So di over dt is going to be positive. Okay, so if we look at our loop equation, this actually makes sense. So if di over dt is going to be positive, then the EMF of the battery, or I'm sorry, I misspoke. So the voltage across the inductor is going to be positive on this end, it's going to be negative on this end, and that's why we do minus L di over dt on the loop equation. So now let's set up the differential equation, and I'll solve it as well, because we had to do for part 2. So here we need to separate our variables. All right, so I have L over R times di over dt equals epsilon over R. So what I'm doing at this point is just all the algebra steps to set up our equation. So I just divide everything by R. Okay, and actually I skipped a step here. So it's L di over dt is equal to epsilon minus IR. Okay, so I go from here, then to here, and then we're going to divide everything by R. All right, then I can move the dt to the other side. So I'm going to multiply both sides here by dt. I'm going to start working on this side. So I have di over epsilon over R minus I. All right, so what I did is I took this here. Okay, so I divided both sides of the equation by this, right? Put that under the denominator for di. And then this part over here, the dt, and the L over R, right? So this whole part over here, I'm going to move it over to this side. Right, so just to clarify the algebra steps, I'm going to be skipping a couple steps here and there. So I have this expression on the left-hand side, and the right-hand side I have R over L times dt. And then what we have to do, we have to integrate. But before I integrate, something else I want to do. So notice I have a negative I over here. All right, so you can integrate it straight up, but then you're going to have negative. So like the integral of 1 over negative x is going to be negative ln x. I think it's easier to think about just keeping this quantity that we're integrating, keeping it positive. So I'm going to do is I'm going to multiply both sides of the equation by -1 before I integrate. All right, so then basically I have di over I minus epsilon over R. Right, so I multiplied the left-hand side by -1, effectively switching the order of the denominator. And then now I have negative R over L dt on the left-hand side. And finally, we're ready to integrate, and we have our negative R over L on the right-hand side, which is what we should have. So I'm going to integrate these. Okay, R over L are just constants. And then in terms of our bounds of integration, I have 0 over here, because the initial current is 0. and then I have I as a function of time. Over here is our upper bound, and then here we're just going to integrate from 0 to t. Okay? And then when I perform the integral, all right, I end up with ln x, or ln I technically, or the I minus epsilon over r. So my upper bound is going to be I sub t.
All juniors should be moving to their session 1 for the career breakfast.
Okay, so anyways, I have ln I sub t, or I as a function of time, minus epsilon over r. And that's my upper bound for the integral on the left-hand side. My lower bound, so we have to subtract the lower bound, that's going to be when I is 0. So in this case, I just have ln of negative epsilon over r. Okay, and then on the right-hand side, well, the integral of dt is just t, right? And then if I go from upper bound to lower bound, right, that's just t and then minus 0, right? So I just have negative r over L times t. All right. So now what I'm going to do is I'm going to combine these two natural logs here. So now I'm going to be moving from here to over here. And I have ln of I sub t minus epsilon over r, okay, divided by negative epsilon over r, and that equals negative r over L times t. And then I'm going to remove the ln by doing e to the ln, right? So I'm going to treat these as exponents to e, right? Because e to the ln of x is just x. So now I have I sub t minus epsilon over r over negative epsilon over r is equal to e to negative r over L times t. All right. And we're almost done. So now I'm going to multiply both sides of the equation by negative epsilon over r, and I'm going to add this epsilon over r over here. All right. So I'm going to have my final expression is I sub t is equal to negative epsilon over r times e to negative rt over c plus epsilon over r. And then I can factor out that epsilon over r times 1 minus e to negative rt over L. Oh, I put C, I'm sorry, L. So the L looks like a C. So it's inductors. So this is my final expression. All right, so that's RT. Let me clean it up a bit. So it's e to negative RT over L. You can also write it as e to negative t over L over R. Okay, that's also fine because the time constant, right? So normally when we have these differential equations, we have some function e to negative t over tau, and the time constant for an LR circuit is L over R. So you can write it like that. That's totally fine. You don't have to write it like this. But that's basically how you set up the differential equation. It's a little different in the scoring guidelines, right? But I want to show you how I think is the easiest way to approach it. And then you can look at how it's set up in the scoring guidelines. So now we have to look at we're going to close switch X, and we're going to look at the charge of the top plate as a function of time, right? So I know that the charge on the top plate, as soon as we close this, so we open switch X, we close switch Y. Now I have an LC circuit, and it's going to oscillate back and forth. Again, we're going to, this whole first FRQ, we're exploring as a lab today to really make sure we understand it. So I'm going to be rather brief here. And we have to highlight any important features. All right, so immediately after the switch is closed, okay, I have current that's flowing through the inductor, all right, and the inductor is going to want to maintain the current in that direction. All right, so that means that the charge on this plate, right, so in order for the inductor to maintain current in that direction, so the current's going in this direction, okay, then it's going to flip where this is going to be positive and this is going to be negative in order to maintain this current in this direction, right? So that's what the current is through the inductor at steady state. And then as soon as I open switch X, close switch Y, I'm going to have current flowing through the capacitor in this direction, all right? So it's asking about the charge on the top plate. So this is the top plate here. And since current is flowing this way, this plate is going to be positive, and this plate is going to slowly become negative. So that's what's important for this graph. We know it's going to be a sine wave, and we're going to see that in the lab today, but it's going to be a sine wave that looks like this. All right, so here, let me draw my sine wave. Okay, it goes down, up, and back down. And this is not the most beautiful sine wave, but it's a sine wave. Okay, so there's my sine wave. And then the important feature here is that after one complete oscillation, right, so the period of an LC circuit is 2 pi times the square root of LC. So we have to highlight that here on this graph. So this value here is 2 pi times the square root of LC. That's going to be one complete oscillation of the circuit. And then we have to derive an expression for Vmax. When you're doing LC circuits, the expression that you're going to use, or the way you're going to analyze it, is through energy. So I have the potential in the inductor. Initially, all the energy is in the inductor, all right, but that energy is going to flow back and forth between the inductor and the capacitor. So what I can do is I can compare the energy of the inductor to the total energy of the capacitor. So whatever the maximum energy of the inductor, that's going to be all the energy of the system. And then at this point here and here, okay, that's when the capacitor has all the energy, because remember the equations. So the energy of a capacitor, so for a capacitor is 1/2 CV squared, right? And then for the inductor, it's 1/2 Li squared. That's going to be for the inductor. All right, so I know that the maximum energy they can have has to be the same. So I'm going to write that out. So 1/2 CV max squared equals 1/2 Li max squared. And I know that the current, the max current is just epsilon over R. The reason I know that is because I'm looking at this circuit here. When it reaches steady state, the inductor just acts like a wire. So there's not going to be any potential drop across the inductor. And then all the current in the circuit initially was just going to be the voltage drop across this resistor, right? So the current I is equal to epsilon over R, because at steady state, this inductor acts like a wire. All right, so going back to here, we have this expression. And then we just got to solve for the max current. So I know that I can multiply both sides by 2. So C Vmax squared is equal to L times epsilon over R, quantity squared, right? So I do a substitution here. And then I'm going to divide both sides by C and then take the square root. So then my expression for Vmax is the square root of L over C times epsilon over R. And that's how you do the first one. So the next one, we have a wire, and the current varies with respect to time. So I have this function that tells us about the current. Let's see, let's mark this up. All right, so I have this expression that tells us about the current, and I have a square loop here that's has a side length of S, and it's 3 side lengths away from the wire. So the wire is going to generate a magnetic field around it, and there's going to be some magnetic flux through the square root loop. Importantly, the magnetic flux through the square root loop is going to change. All right, so that's how we're going to approach the first one. Here we have to draw arrows indicating the direction and magnitude of the magnetic forces. So let's understand what's going on. As here, the current is increasing with respect to time. Use your right hand rule. So thumb is direction of current, and the direction that your the fingers on your right hand, that they curl, is going to be the direction of the B field. So on the left hand side of the wire, I have the B field coming out of the page. Okay, so the B field is coming out of the page here. Okay, and then on the right hand side of the wire, the B field is going into the page. Okay, and the magnitude of the B field decreases as we go out. All right, here in the wire, I'm also going to have some B field. So I'm going to just draw some B field here. And if I have magnetic field going into the loop of wire, and that magnetic field strength is increasing, since the current is increasing for the wire, then I know that I have a magnetic flux also pointing into the square loop. And that magnetic flux is going to be increasing with respect to time. All right. So Lenz's law, we're going to be using Lenz's law to determine the direction of the current. And I know that the EMF induced in a loop of wire is equal to the negative change in magnetic flux over time. So the magnetic flux, right? So I know the magnetic flux is going into the page, but it's increasing. So the direction of the magnetic flux, like how it changes with respect to time, is also going into the page. Okay, so this is also going into the page. This is analogous to, I think a good way to think about it is that if I have a velocity vector and my velocity is increasing with respect to time, that means my derivative, right, has to be pointing in the same direction, right? So it's like I have a positive acceleration, positive velocity, my velocity will be increasing, right? So that's important to note. So that means that this is going to want to generate a current that produces a magnetic field going the other way. So this is the magnetic field from the induced current inside the loop of wire. So in order to generate a magnetic field going this way, right, we understand that the current has to be flowing in the counterclockwise direction. So the current in here, let me use a different color, the current is going to be going this way. Okay, because that's what's going to generate a magnetic field that opposes the change in magnetic flux. All right, so Lenz's law, another way to think about it, outside of the mathematics, is that nature doesn't like change. So I'm changing the magnetic field in this square loop, and it's going to oppose that change. So it's going to generate a current. The EMF generated from Faraday's law, it's going to generate a current that's going to want to oppose that change in magnetic flux. So I know that I have a current going clockwise. Finally, in order to determine the force, you have to use the right-hand rule again, right? So your thumb is the direction of current. Your index finger is the direction of the B field. And then your middle finger is the direction of the force, right? So the net B field inside of the loop of wire is still pointing into the page, right? So I have a B field in terms of the force, right? I know it's ILB sine theta, right? So we take a cross product, they're at a right angle. The current is going up, the B field is pointing into the page. So if you take your right hand and you look at the middle finger, that's the direction of the force. So we know that here, the force is going to be going to the right. Here at the top of the loop, force is going that way, and here at the bottom of the loop, force is going that way. So I'll put that all inside of the diagram, right? So I have this here. Okay. So those are the directions of the forces. Now we have to have some arbitrary distance that the square loop is away from the wire. And for this, we need to derive an equation in order to figure out what the, actually, is that for, yeah. So that's for the later part. Here, the loop is held in place. For part B, we have to do it in terms of S. All right, so let's solve for this in terms of S. Whoops. So we're still doing this first part, where it's a distance 3s away. So for this first part, I know that the current inside the inductor is just epsilon over R, and epsilon is equal to negative dB over dt. And I know that the current that's induced, we're going to use Ampere's law. So right, so this is the induced current. Okay, and our Amperian loop. So if I have a loop of wire, okay, so the Amperian loop for a wire is going to be a circle. All right, so the Amperian loop is a circle. Okay, and the length over which the magnetic field is tangent to that Amperian loop, it's just the circumference of a circle. So it's just 2 pi r. All right, so basically, when you analyze Ampere's law, you have B times 2 pi r is equal to mu naught times IW. So this IW is going to be the I in the wire, right? So yeah, so that's IW of T. All right, that's what's generating the magnetic field that's going into the loop. It's the current in the wire. So now I'm going to rewrite IW as beta times T. So I know that IW is beta times T because that's what it says in the problem. It's increasing with respect to time. So my B field is equal to mu naught times beta times T over 2 pi r. All right, and I know that the magnetic flux through the loop of wire, we're going to do integral B dot dA. All right, and I'm going to have to rewrite A in terms of the lengths here, right? So my A here, as I move out, so keep in mind that the magnetic flux, it's going to be the magnetic field stronger on the left-hand side than on the right-hand side because the magnetic field decays with 1 over r. All right, so the way I'm going to write this is that the magnetic flux is equal to the integral of mu naught beta times t, that's the current in the wire, over 2 pi r, times our dA term, and our dA term is going to be, so we're some, this A, this area here, okay, is going to be S times dr, okay? So here, this length, this side is S, and the dr vector is this way. So that's my dr unit vector, and I'm integrating horizontally across this loop, all right? And so the area is this side length S times dr. So that part's important when you're dealing with these kind of problems. And then what I can do, S is just a constant, so we can set up our integral. I'm going to remove all the constants. So mu naught times beta t times S over 2 pi times the integral of dr over r from 3s to 4s. So keep in mind that we start integrating a distance 3s away, okay, all the way up to 4s. So this has to be a distance of 4s because the side length is just s. So those are my bounds of integration. And I end up with mu naught times beta times t times s over 2 pi times the ln of 4 over 3. All right, almost done. So we're trying to figure out an expression for the current induced in the loop. All right, so this is our magnetic flux. So now we have to look at our change in magnetic flux with respect to time. All right, so our change in magnetic flux with respect to time, we just take the first derivative with respect to time. That's going to be easy because there's just a t here. All right, so my first derivative is mu naught. The derivative of t is just 1, okay? So here I have beta times s over 2 pi ln 4 over 3. Again, the t disappeared because we took the derivative, right? So derivative of t is just 1. And then I know that the current in the loop is equal to, well, the EMF over R. We're just going to look at the absolute value of the current, right? Don't worry about the minus sign because it just tells you if it's going clockwise or counterclockwise. So I know that Faraday's law, EMF is negative d, the negative change in magnetic flux with respect to time. But I'm just going to write this as 1 over R times the change in magnetic flux over time. And you're going to see this in the scoring guidelines as well. I'll post those along with the video since I'm moving through this rather quickly. Times beta s over 2 pi r and times the ln of 4 over 3. And that's my final expression. So now what we need to do is we need to look at the magnetic flux magnitude, right? So here we're looking at some later time. So we're comparing T1 to T2. Well, you have to understand that if we look at our equation here, oh wait, so now this is for some arbitrary distance dl away from the wire, and then we have to look at it as a function of dl. So here, let's derive what that has to be. So instead of s, we're dealing with dl. So I know the magnetic flux for my earlier expression is beta t times s, where s is the length of the side over 2 pi. And I'm going to integrate. So again, I'm integrating across, right? So I at some distance dl apart, and then at this point, I'm at a distance of dl plus s. So I'm going to integrate from dl, okay, so that's lowercase l. So that's dl to dl plus s dr over r, okay? And the integral of that is just ln r. So I have, and then when I do upper bound minus lower bound, and then you're going to look at the ratio, because that's how you treat the addition or subtraction of logs. for the sake of time, since I'm running out of time before pride block, I'm just going to write the final expression. So I have dl plus s over dl. All right. So anyways, here I need to graph this function. All right. And I know that I see that this function is, well, obviously it's a natural log. But with respect to time, okay, at a later time, the magnetic flux is going to be larger, right? So I see that as time goes on, because the current through the wire is beta times t, the magnetic flux is going to be increasing with respect to time. So here we're looking at the magnetic flux magnitude as a function of dl. So now I'm looking at it as a function of dl, okay? And I can see here that as dl increases, the magnetic flux is going to decrease, all right? And it's going to follow the natural log. So it's going to look like ln x, right? So you need to know what the functions generally look like, because you're going to have to be drawing sketches. So you have to know that ln x is going to be like this. It's going to be approaching infinity, right, as it approaches 0. So I'm going to draw a curve like very close to the axis. And then here, this is my first curve at t1, and it's going to asymptotically approach 0. So this is t1. And then t2 is going to be slightly above t1. And the reason for that is basically it has a larger coefficient, right? So if I look at my function here, right, we see that at t2 is going to be greater than t1. Then it's basically just multiplying it by a larger coefficient. So it should be above t1. And that's it for, part D. Is it, so how would it be different at all? So in a new scenario, the straight wires, okay. So now this case, we're flipping the direction of current. And if you do the analysis, so instead of the current going up, now the current in the wire is going down. So now the magnetic field is going to be pointing into the page. But if you do all the analysis again, okay, you're going to see that you end up with the same result. You're still going to end up with forces that point in this direction. So I'll let you all do that. And I want to move on to the last one, right? So again, I'll post all these scoring guidelines. For the third one, it's just an experiment with changing magnetic flux. I want to focus more on the circuits. So here for the final FRQ, we'll review. This one is not too bad. So here we just have an LR circuit, and we need to look at how the magnitude. So we're going to initially going to close the circuit, complete the circuit, and now current's going to flow. So current's going to flow. So current's going to flow from the battery through the resistor, through this resistor here, and then some of it will flow here. But at t equals 0, right? So at t equals 0, the current through the inductor is going to be 0, right? Because the inductor opposes that change in current. So we're comparing when the switch immediately closes for when the switch is then reopened at a later time. So when the switch is immediately closed, I'm going to write out all the work here so that we can answer multiple parts at the same time. But basically, I know the current in the inductor is 0 at t equals 0. So the current, we're comparing the potential difference across resistor 2. So I know that the current flowing through resistor 2 when the switch is closed, so the current flowing through resistor 2 is going to be the EMF of the battery over R1 plus R2, because basically there's no current going in the rightward branch, and I just have all the current flowing through R1 and R2 at t equals 0. So this is going to be the current through resistor 2. And they also write out that the expressions are, so this is equal to R naught, and resistor 2 is going to be greater than resistor 1, labeled as N R naught. So here I have epsilon over R naught plus N R naught. Now the switch is closed. It reaches, or actually, here we got to solve for the potential difference. Okay, so we have I R2 times N R naught. All right, so I have epsilon over R naught plus N R naught times N R naught, and that comes out to N over 1 plus N times epsilon. Okay, so this is going to be the voltage across resistor 2 at when immediately after the switch is closed. So it reaches steady state. And then the switch is opened again. And immediately after the switch is opened, I'm I know that there's going to be no current flowing through. So when it reaches steady state, so first thing, at steady state, this inductor acts like a wire. So this inductor is going to act like a wire. So the inductor acts like a wire. And what I mean by that is the current is no longer changing. So since the current is no longer changing, there's no longer an EMF across the inductor. So it's shorting out resistor 2. All the current is going to be flowing into the inductor. And then immediately when the switch is reopened, I have just this circuit here, right? So now the inductor is going to want to maintain that direction of current. So now the current is going to flow from the inductor into this resistor R2, right? So that's what's different about this situation. So now working out the math, I have IR2 is going to equal the current in the inductor immediately after the switch is open. Okay, so it's going to equal epsilon over R naught. And then, so we write the expression as VO2. So this is the potential difference across resistor 2 right when the switch is open. I have IR2 times R2, which we know is NR naught. Okay, so I have epsilon over R naught times NR naught. The R naughts cancel, and I just end up with N times epsilon. So this is, if I compare these two values, I know that the potential difference across resistor 2 immediately after the switch is closed is going to be less than the potential difference immediately when the switch is opened. Okay, so here I know the denominator 1 plus n has to be greater than the numerator n, right? So when the switch is closed, only current is flowing through R1 and R2. After it reaches steady state and I reopen the switch, I have current flowing from just the inductor into R2. Okay, and the amount of current flowing through the inductor we see is epsilon over R naught, because basically the current is going to be flowing like this. So at steady state, the current is going to be flowing like this. Okay, and then when the switch is closed, or I'm sorry, when the switch is reopened, then the current is going to be flowing like this. All right, so as you can see from the math, we see that the voltage across the resistor when the switch is opened again has to be greater. So this is the answer. All right, and then the final part, you have to look at the ratio. So we have to derive a ratio and then see if it's consistent. Hold on 1 second. So the ratio is going to be, let's see here. So we got to look at the ratio. That's the last part we have to do. So the ratio of delta V open, right? We know it's going to be greater than immediately after it's closed. So I have N times epsilon over N over 1 plus N times epsilon. And then when you work out all the math, you end up with 1 plus N. And that's it for part B. And then it has to be consistent, right? Because we know that N is positive. Hey, what's up? And the value of 1 plus N is greater than 1, which makes the ratio delta V not 2 over VC2 has to be greater. All right. So it's consistent. That's it for now. I'll post the scoring guidelines along with this, and then you'll see for FRQ number 1, our lab today is going to be just like the FRQ. So we'll have a better understanding of how to set up the differential equation for the IR circuit, or the LR circuit. I misspoke. All right, that's it.